we're given a function from real number to real number. The function is continuous over the entire real number line. We're also told that function is periodic with a period of t, and we want to show that this limit, 1 over x times the changing upper bound integral, is equal to 1 over the period, this definite integral. So first of all, we may think of using L'Hopital's rule, because as soon as we see this expression, we have x at the bottom, we have this changing upper bound integral at the top. Right? Since x is approaching positive infinity, right? But the top, I don't know whether it's approaching infinity or not. But doesn't matter. We can still apply the L'Hopital's rule. Right? That's what it says. Then we get 1 at the bottom. Then we get f of x. So the problem is that if it has a limit, then this will have a limit. But the thing is that we don't even know if f of x has a limit when x approaches positive infinity. It may have or may not. Right? If it doesn't have a limit, then does that mean the original expression doesn't have a limit? I say not necessarily. It just means we have to find a different way of doing it. So here's when I find this way. Right? So first of all, it says x approaches positive infinity. And it's also periodic, the function. Right? We can say as x it becomes big enough, I can let x equal to n times the period t plus x naught, where x naught is greater than 0 and less than t, the period. Right? This is definitely doable. Right? Let n become big enough. So that way my original expression will become this. 1 over nt plus x naught. 0 to nt plus x naught. f of t dt. And this I can split it into two integrals. Right? 0 to nt plus nt plus nt up to nt plus x naught. Right, 2 parts. The same function. Since f is periodic, right, you have integral from 0 to nt. So each period, right, period is t. You have n many of them. Right, it's periodic. So all you have to do is to multiply this area by n times. Right? So x naught. Then you have n times integral 0 to t plus this integral. Right? Since this function is periodic, right, all you have to do is to work out the integral from 0 to x naught. It's the same thing. Right? Because, for example, here is nt. Here, right, this point is nt plus x naught. Right? This area. Right, it's the same as if you start from 0 up to x naught. Right? Same thing. So up to here, right, just multiply it out. Right, we multiply this n over nt plus x naught times integral of 0 to t, f of t dt. Then we multiply this out. Plus 1 over nt plus x naught times integral 0 to x naught ft dt. So when you have a look at this, right, you have a leading term at the top, which is n, leading term at the bottom, which is nt. So all you have to do is to look at their coefficient, 1 over t. Right? That's your limit as n approaches infinity. Right? So 1 over t integral 0 to t f of t dt. Right? So as long as we show that this limit is 0, then we're done, because this is our desire. Right? So this limit, why does it approach infinity? It approaches 0. It's because 1 over nt plus x naught. X naught is a constant, right? It's bounded and approaches infinity. But this definite integral, of course, it exists, right? Because f is continuous.